Chemistry is a very mathematical field, but we treat numbers very differently in chemistry than we do in a mathematics class. There's two things that are a very common part of our life in chemistry that you don't touch in a math class very often, and that is the concept of accuracy and precision and significant figures, and also the use of scientific notation, which we rely on heavily. So let's begin with the accuracy and precision. You can think of accuracy being how close you are to the true measurement of something, which you're kind of at the mercy of the tool you use when determining accuracy. But imagine in a game of darts, you can think of accuracy as your ability to hit exactly what you're aiming for. If you're aiming for the bullseye, did you hit the bullseye? Precision, though, is your level of exactness. You can think about it, if you take numerous measurements, are all of your measurements going to be close to the same? Or in the dartboard example, you can think of it as if you're throwing darts over and over again, do you consistently hit the same area? So back using the dartboard approach to understanding this, you could imagine accuracy if you're aiming for the bullseye as you throw 3 darts and you get 1, 2, 3. Now, we did have the ability to hit what we were aiming for, so we would say that we have really good accuracy. But on top of that, we were able to make the shot 3 times, the same shot, which means we have a close grouping of darts. That also shows precision. So this would have both accuracy and precision, but we could also have an example of neither. Let's say we're aiming for the dartboard and the first one hits here, even though we're aiming for the bullseye. And we're thinking, okay, so that was a little high, a little to the left, so we throw the next dart, boom, down here. Then we go to throw the third dart, and we're like sticking out of the wall over here. Now, we definitely don't have accuracy. If we're aiming for the bullseye and none of these 3 darts were anywhere near it, you don't have accuracy. But not only that, there's very little precision either because the darts are all over the place. We were not able to repeat our shots at all. Now, the next possibility is having one without the other. So let's say we have somebody who throws 3 darts, and we have 1 here, 1 here, and 1 here. Now, if they were aiming for the bullseye, we definitely don't have accuracy, but what we do notice is we have pretty good precision. They're all pretty close together in one spot. So no accuracy, but good precision. Now, there's one last possibility. Maybe somebody throws 3 darts and they land here. At first glance, you might not think they have much accuracy or much precision. And the precision's not great because they're pretty far apart. So we'll say no to precision. But if you consider the accuracy, if you take an average of these 3, the average is right there, dead center of the bullseye, we would make the case that they're very accurate. Now remember, if we take multiple measurements in any experiment, if we get measurements that can be averaged together to give us a measurement that's very close to the true value, that's considered good quality. Now, when might we have a situation where you have slightly different measurements, but the average is good? Oftentimes when you're measuring things with a ruler and they're large items, if you're off by just a little tiny bit, your measurements will look off. But if you repeat yourself many, many times, chances are the average of them is a very accurate count. What we see when we get precision but not accuracy, think about a scale. You get on the scale over and over again, it keeps giving you the same weight. You have a pretty good, precise, exact scale. Problem is then you go to the doctor's office and use their scale, which is also precise, but might give you a total different number than your scale. So there's an error in accuracy here, and that's why I said with accuracy you're at the mercy of the tool you use. But the precision of them is great. You keep getting the same measurement every time you get on it. So the accuracy is tough because it relies so heavily on the tool you're using. However, precision is very important when we are dealing with any data, and we use significant figures to indicate precision. Significant figures are defined as all parts of the measurement that we are very confident in, plus one last digit in the measurement that is an estimate. That tells us basically, is it a little above or a little below that number that we gave. The more significant figures you have in a measurement, the better it is or the more precise it is. take a look at these two rulers to understand. In the top ruler, you only have centimeters. So if we look at the length of the paper clip, I think we all agree it's greater than 2 and less than 3. You don't want to tell somebody that it's a 2 centimeter paper clip because it's not 2 centimeters, it's more than 2 centimeters. So what we do is we come up with an estimated digit that tells us what we think it is so that people know it's not exactly 2. Now, what if I say this is 2.3 centimeters and somebody else says it's 2.4 centimeters? Well, honestly, that's not a big deal because they both give us the same rough idea. They both tell us that this is a measurement that's greater than 2 centimeters and that it's also less than halfway between the two measurements, which is good too. Okay, so the level of precision we have here is based on two significant figures. If we look at this ruler, you see the paper clip is at least 2.3 centimeters, but it does not reach 2.4 centimeters. So at this point, you have to kind of look at it and decide, well, is it halfway between them? Is it a little less than halfway between them? I think it's just slightly halfway between them at 2.34 centimeters. But if you disagree with me and you say this is 2.35 centimeters, we're both still right because they did what's intended. They told us that it's greater than 2.3 centimeters and less than 2.4 centimeters, and then they estimated the last one as close as possible. This one gives us 3 digits to our measurement, so this is a more precise measurement than this one. Think of it, the more numbers you have in the measurement, the more precise it is. So how do we count significant figures? Well, let's break them into 2 different types of numbers, non-zero numbers and 0. Non-zero numbers are always significant. The zeros are a little dicey. If the 0 is sandwiched in between other numbers, it is significant. If it's a leading 0, meaning it's in a decimal at the front of the number, it's never significant. Those are either just placeholder zeros or they're there to get your attention so you notice the decimal point. The trailing zeros are the most difficult and confusing. The trailing zeros are the ones at the end of a number. Sometimes they're significant. If the trailing zero is at the end of a whole number and there's no decimal point, then it means they weren't really measured. They're just there to tell us the size of the number. They're placeholders. Those are not significant. If we need the numbers at the end of a whole number to be significant, then we put a decimal point at the end, and those zeros at the end of the number become significant when there's a decimal point after them. And the last one, if they're trailing zeros that are pushed back after a decimal point, they're significant because they're telling somebody, yes, this was measured. It's not an estimate, it's not a placeholder, it is part of the measurement. So again, non-zero digits are significant, sandwich zeros are always significant, leading zeros are never significant, and trailing zeros depends on the situation. So let's look at a few examples. In this one, non-zero, non-zero, they both count. Sandwich zero counts, non-zero counts. These two do not count. They're at the end of the number and there's no decimal point. So this would be 4 sig figs. This number, 45,000 point joules, these trailing zeros don't count because there's a decimal point after them, so this is 5 sig figs. This one, my 2 leading zeros do not count. The 6 and the 5 do. The trailing zero counts because it's after the decimal point, so that gives us a total of 3 sig figs. And in this one, 56.35, those are all significant, and this is a trailing zero after the decimal point, so this counts, giving us 5 sig figs. Next one, leading zeros do not count. The 2 does, the sandwich zero does, the 1 does, and the trailing zero at the end after the decimal point counts, so we have 4 sig figs. This one, 125.00, is 5 sig figs. Our trailing zeros count because they're after the decimal point. Okay, so when we're rounding, we base things on sig figs. So we decide how many sig figs we want or need, and we start at the first significant figure and we count over until we get through all of them, and then you look at the digit that's after the last digit. If whatever number's after the last digit is less than 5, keep that last digit the same. If it's more than 5, bump it up to the next number. But if it's 5, we treat it differently depending on the scenario. If it's 5 followed by other stuff, bump it up. If it's exactly 5 after that last digit, we really don't know if the person rounded it up to 5 or down to 5, so we just have an arbitrary rule that says round it to the even number. So let's look at these examples. Number of sig figs to keep, 3. This is not significant, so I start counting here, 1, 2, 3, and I cut off the rest. The 3 is followed by 5, but there's stuff after the 5, so I round it up. So it's 0.654 centimeters. In the next one, I want 4 significant figures, so 1, 2, 3, 4, and I cut it off there. This 8 is followed by a 9, so that goes up to a 9. Now remember, when you round, you want the meaning to stay the same. So this is not 9,579. We want it to remain 95 million, etc. So what I have to do is in any whole number where I cut numbers off before the decimal point, I have to use placeholder zeros to fill in. So this would be 95,790,000. The next one, we want 5 sig figs. This is significant, so we count 1, 2, 3, 4, 5 and cut it off there. Now this one is a decimal, so after the decimal point, we do not need placeholders. This simply becomes 44.763 joules. The next one, we want 3 sig figs. 1, 2, 3. The 5 is followed by a 1, so the 5 stays the same, and we end up with 78.5 liters. In the next two, we see that one rule that's a little different in chemistry. We want 3 significant figures, so that's where we cut it off. Now in the first one, we have 65.15. It ends with exactly 5, and we're just removing that exactly 5. The rule is round to the even number. So 1 is odd, we round it up to 2, and it becomes 65.2 watts. In this one, we have 65.25. The 5, again, exactly 5 means we have to round this to the even number. 2 is even, 3 is not, so we'll leave it at 65.2 watts. And the last one, we want 4 sig figs. We don't start counting till the 5, so we go 1, 2, 3, 4. We're getting rid of exactly 5, so it becomes 0.005032 millivolts. Okay, the whole purpose of learning to count sig figs and learning to round is so that we know how to handle calculations. Remember, we are humans. We are the ones taking the measurement. There is always going to be some error in our measurements. We are not perfect. So, keeping that in mind then, we can't do math with imperfect numbers and get a great number at the end. So the whole purpose of rounding is to get rid of the numbers we're not really sure of that don't really mean anything at the end of the number. For example, if we're multiplying these two measurements together, in each case, you have an estimated digit. The 3 is estimated, the 5 is estimated. So when we multiply these together, we can't report our answer as 127.825 centimeters squared. Most of this is garbage because we don't have a lot of precision in the numbers we started with. So our rule for multiplication and division is you start with how many sig figs are in each measurement, and then round so that it matches the one with the least sig figs. So we have 4 sig figs here, 2 sig figs here. My answer should only have 2 sig figs. So if I round this to 2 sig figs, that 2 rounds up to a 3, and I need a placeholder 0 to fill in for this, and it becomes 130 square centimeters. These sample problems are done in much the same way. We begin by counting the number of sig figs in each measurement. For 285, that's 3. 2.00 is 3. 15.00 is 4. And 8.21 is 3. So looking those over, it seems like 3 is the fewest number of sig figs. That's what will be in my answer. I've already plugged this into a calculator, and the answer I get from the calculator is 1.15. 7125, 451. With only 3 sig figs, we're cutting it off after that 5. This 7 causes it to round up to a 6, 1.16. And the unit, which we have to do algebra on, is grams on top. On the bottom, centimeter times centimeter times centimeter, which is centimeter cubed. This is a density measurement. In the next one, I have 5 sig figs, 2, 5. 2 is the fewest. I will only have 2 in my answer. And again, I already calculated this to be 12,741.114. If I want only 2 sig figs, I'm cutting it off there. Notice the decimal point's all the way over here, so we'll need 3 placeholder zeros to get us to the decimal point. So this will become 13,000 centimeter times centimeter times centimeter, 13,000 centimeters cubed. Okay, so that brings us to addition and subtraction next. And when we're adding and subtracting, we still say that we're rounding based on sig figs, but we're not actually counting sig figs for these. You're going to count decimal places instead. When we line up numbers the way we learned how to do it in math class, it makes good sense why we're using decimal places. So I'm going to do that. If I take the 51.13 centimeters and add 2.5 centimeters, keep in mind that this 3 right here is an estimated digit, but so is this 5. So if I add them together, we get 53.63 centimeters. Both of these are estimated. I could only have 1 digit that's estimated, so that means we're going to get rid of the last one, and my answer becomes just 53.6 centimeters. So our rule for adding and subtracting is instead of counting the sig figs, we count our decimal places, but we do the same basic idea, which is keep the number of decimal places in whichever number has the fewest decimal places. So take a look at this example. The first one, I have 2 decimal places, 1 decimal place, and 4 decimal places. I want 1 because that's the fewest. And again, I've gone ahead and done this calculation. I got 383.4103, and I want only 1 decimal place. So I'll cut it off at 383.4 grams. In the next one, I have 3 decimal places, 1 decimal place, and 0. So the fewest number of decimal places is 0. When I add this together to get 39.551 kilometers, and I want 0 decimal places, that's going to force my 39 to go up to 40. Problem is, I want everything here to be significant, but I don't want any decimal places. So the only way I could do that is add a decimal point there, and finish it off with kilometers. What you notice again is in multiplication and division, just like in algebra, we have to do math with the unit. When we're adding or subtracting, the units have to match, but we don't do any algebra with it. It's grams plus grams plus grams is still just grams. Kilometer plus kilometer minus kilometer is still just kilometers.